Hello, my name is Arya Shahdi. I'm the author of SPVAX, a fully optimized SLE thermodynamic modeling software for paraffin. In this video, I want to talk about main functionalities of SPVAX and perform two practical examples in binary and multi-component systems. So before I run the program, let's go to the directory that our package is located at. So in here we have several files. So in order to run it, we have to click on exe file spvax run. So as you can see, all of these files should be present in the same directory to be so it can run. So within all of these, we have 3 PDF files, some .exe files, and this text file as some input information. So to bring up the main SPVAX software, we have to click on SPVAX int, which is the interface. So when it is open, we have two options: multi-component system and binary system. Let's go to the binary system first. So before I go through binary system and multi-component system, let me talk about two options that we see over here. First, whatever input value that you put, okay, you can save it. Then you can open it up for a later time, so you don't have to provide input data every time that you want to run the program. Second thing is that you have some options over here. You have user's manual. So user's manual is here. It takes any user to use. It takes every users to different sections of our program. And the second one is the developer's manual. So this file, which is 6,000 words, are about thermodynamic model itself, which is for developer's point of view and developer's interest. And you have the licensing statement, and we have the contact information. So me, Arya Shahdi, and Dr. Panacharoensawad. So we will be happy to answer any question. So let's go to the binary system first. So in binary system, we have two inputs. So let me try to open up so within the directory, so we have a file which is called save runs, shown result in the paper. We're going to go ahead and click on that, the binary, and you can choose whatever. So we chose 25C7. So then we have main run. So it fills out these two solvent and solute carbon number. So for solute mole fraction, okay, so in solute mole fraction, we provide the solute mole fraction that we want to calculate the solid solubilities for. So we open up this case and put the solute mole fraction, apply, then okay. So for experimental data, the same. We provide the experimental solid solubility and data points. We click apply, then okay, and then we run the program. So when we run the program, the C# interface go ahead and call the binary exe file, which has been developed in C++, and this is how the communication between C# and C++ works. So I think our program is done, so we're going to go ahead and close this. I think it's done, and then we can plot the data. So when we plot the data, simulation versus experimental data, then we can save it, and we save it if the picture is saved over here. That okay, we don't want to. Let me close it. Okay, so just get it for now, and let's go to the multi-component system. Let me close the binary system case, and let's go to multi-component system. So in multi-component system, you have program categories. So first of all, if you have any, if you don't know the meaning of each input, you always can go to developers and in user's manual to get all information about all of these input parameters. However, I made it possible that when you click on, if you keep your mouse on any of the input parameters over here, a box tells you the information about each one that you want to know. So first of all, so when you talk about multi-component system, you have a mixture that contains contains alkenes, for example, petroleum mixture. So in that case, we want to know the precipitation curve. So for precipitation curve, I also have saved file. Let's go to the read around case, which are presented in the my paper, and we're going to choose that case. Next, the most important one is the N-alkene normalized mole composition of the N-alkenes. We're going to go ahead and choose them as well. Okay, so it fills it up. You can plot them, then apply the video. Okay, and if you have experimental data to plot it against, so you go ahead and choose your experimental data as well. So the experimental data are provided over here, and we click apply, then okay. So you see the run and plot buttons are freezed. You have to choose K initialization first. So in this program, in all SLD calculations, in high temperatures, you usually have convergence problem. So by this click, okay, we provide some initial values for our oil sample as initial guesses for K values. So when we click on that, it's going to produce the K values and going to restore it in text files, in a text file. So now it's run. We run the simulation for precipitation curve. So for all these cases, there is an extra section as comments to explain what all parameters are, and we found it really helpful, especially for non-technical users. And then when it's done, we can plot it. So as you can see here, precipitation curve is plotted against experimental data. And then also you can plot the composition, solid phase composition at a temperature that you wanted, in the temperature range that you gave in this section. So again, to get familiar with all of these inputs, you can go to the user's manual or just stand over there and read it from. Okay, so let's go to the next one. So in many cases, we want to know the SLE properties at one instance temperature. So in that case, we made it possible. We gave a program category which is called one temperature SLE calculation. We click on that, and then over here we have to give the temperature. So let's give it 280.23. So we don't have to click on K initialization now. We just run the program, and then we can choose whatever we want over here as mole composition, weight composition of solid liquid phase, equilibrium constant, and dissolved mass. So let's choose equilibrium constant, then we can plot it. So when we plot it, a comment related to the chosen output parameter is going to be popped up or appear, and also you have the solid wax weight fraction in that temperature in this graph. Okay. The last option of our program in multi-component systems, okay, is the critical carbon number. So critical carbon number is a concept, okay, borrowed from wax deposition in pipelines. So we talked about it in our manuscript and in the user's manual. In developer's manual, you can go and we have a set of equations. However, here we can give a very good approximation for critical carbon number based on two temperature information. One which is in deposit interface, talking about the wax deposition inside the pipe, and one at wall temperature. So that's what we have to give. And I have another case ready to open up, and for example, we open this one up, run the simulation. Okay, now then we plot it. So the first positive relative concentration gradient, the first carbon number with positive relative concentration gradient is going to be CCN, or critical carbon number, and it's reported over here. So if you have any more questions, please let us know, and thank you so much for using our software, and have a good day.